Okay, the first step in creating this robot simulation was to create a 2-axis simulation in Simulink, and we converted all of the axes to be in the same frame, and then we finally got this, and this allowed our robot to follow its work envelope as it's rotating now.
The second step in developing our self-balancing robot was to derive the Lagrangian dynamics of a pendulum. We initially calculated this in terms of torque, then converted it into voltage as our input from our DC motor. We added friction effects and ended up with these final Lagrangian dynamics. We then had to insert constants for resistance and some motor constants, calculating all of the thetas or parameters of our machine. The next step of developing our self-balancing robot was to perform a system identification. The purpose of this was to get better estimations of the physical parameters of our robot. These would include things such as the friction at joints, or the moment of inertia of each arm. So in the last step, we used the Lagrangian dynamics. In this step, we will be using the Hamiltonian dynamics. The biggest difference is that we are doing the kinetic energy plus the potential energy instead of the kinetic energy minus the potential energy. The big point of this is that it uses the conservation of energy. This changes our Hamiltonian to this equation here. We then separate it up into smaller h's, so that each one would correspond to an independent theta or system parameter. And we also have an F matrix, which is going to be the integral of the square change in our second arm. We then put them into two different matrices, A and a D matrice. And the F is going to be the friction. And from this, we can calculate the theta using this equation here. In order to put this all to use, we made our robot flail wildly around randomly so that we could make sure to get the full dynamics of our robot. It took about 10,000 points of data and applied this equation to it.
Okay, our next step was we had to create our hybrid control, which is a switch in our simulation, but it controlled where our states would change. So if this is our stick can only go from state 1 to 3 and then back to 2. And we used our code with a bunch of if and else statements to make sure that this happened. And 1 would be swinging up, and then 3 is it balancing. And when it's knocked off its balance, it would go into 2 and then go back down to 1. And in our code, we set restrictions on the velocity, so it would basically come down to a slow enough point in 1 where it would be able to swing back up and not go out of control.
The first stage of our self-balancing robot was the swing up portion. In order to implement the swing up portion of our self-balancing robot, we decided to implement a PV controller, proportional and derivative. And in order to calculate our proportional constant and our derivative constant, we first needed to choose some response constants for the time domain. We chose 5% for an overshoot and a time to peak of 150 milliseconds. From these numbers, we can calculate the damping ratio and the natural frequency in the frequency domain and assume a second order transfer function for our system. And going back to our block diagram for the PV controller, we can follow it to create a closed loop transfer function that looks something like this. And now going back to our assumed second order differential or second order transfer function, we can create equations to calculate our proportional constant and our derivative constant, giving us 12.1 and a very small -8 times 10 to the -4. The next thing that we had to do was also give it a target. We call this Q1D, and we did this as calculating the a linear superposition of Q2 and Q2 dots. We didn't really have any way to calculate K1 and K2 other than by trial and error. So if we go back to here, we can show you what we ended up with. We had to add a saturation block because we wanted to keep things in the what's that called? We wanted to keep things around the equilibrium points of being balanced. So we added a saturation block, and using trial and error, we got 0.7 and 0.02 for K1 and K2. For the balancing state of our self-balancing robot, we decided to use a P controller or a proportional controller. This requires that we calculate a K, which is a proportional feedback gain. To do this, we started out with our nonlinear dynamics. So the derivative of our states would have 4 nonlinear equations. We then linearized these equations by taking the Jacobian, which means that we created a matrix by taking the partial derivative of each function by each of the respective states, and also each function according to the input. We then took these matrices and put in our equilibrium point, which we defined as 0, 0, 0 by creating Q2 equals 0 at the top. From this new linearized system, we now have an open loop, which we can calculate our eigenvalues or the poles. This will determine the stability of our system. What we got were these numbers here, and we have a positive eigenvalue. And if we go and look at this real and imaginary graph, any poles that are in the right half plane of the graph are going to be unstable, making our system unstable. If we have anything that is far away from the real axis, we will see some oscillatory behavior in our system. Far left we place our poles, the more responsive they will be. The closer to the origin we place them, the less responsive they will be. So we need to find some happy medium so we don't max out our inputs. So we used the place command in MATLAB and chose some poles to place, calculating some gains, which we could then place into our P controller, letting us balance our robots.
So when finalizing our robot, we had to implement a fourth state. So if our balance was interrupted from a position far from Q1 and we tried to do the swing up again, then our system would not swing up nicely. So we had to implement the reset state, basically where we're taking the Q1 position and then we are putting it in a P controller and multiplying it by a gain of K equals 1 to bring that location back to 0 and it can swing up. Okay, so now we have our final robot, and to make sure that it can perform all the types of swing ups, we have a set of controls here to change Q1 desired with these switches, and we'll have different inputs. We'll have a sine wave, and we also have a constant, which is controlled by this this slider gain, so we can move this and change the position of our pendulum. And then here also we can use the force and move this ball on this, what's this, resistance track? It's like a resistor. And it will follow this ball movement up here. So I guess first let's demonstrate just with the constant slide. Ready?
Mm-hmm.
Okay, now if the balance is interrupted, it should fall and slow to a certain velocity that we set here, and then should swing right back up.
I'm gonna upload my I'm gonna do my variations in a couple of seconds. I'm gonna upload my stuff. But if we have to record, we don't have to have anything early. We just have to have what you have. What else do we have to
You stop that one. Okay, now we're gonna show it with a sine wave input to make it dance. And now if we control it by the slider, by switching this back. We can slide it around.
You gotta let go.
Oh, I let go. Okay, hold on. I can do that. Nice, nice. Okay, and then if I add this, put this back to a constant 0. Go back to 0. And then if we switch this over to our read analog, we can follow the ball.